Okay, this is the last assembly language talk on digital logic. We're going to look at a simple finite state machine example so that you can understand things a little bit better. Actually, maybe a couple examples. So here we have basically essentially what we had before with the inverter. This little bubble with the AND gate, as long as that's a 1, is like that inverter. So this now has the addition of an input. You can turn the whole thing off here. If you put a 0 on this line right here, 0 and whatever this is going to be 0, which will keep the light off. But if you turn on this switch, then some interesting things can happen. So let's just suppose the state we come up in when we're start out with is this is a 1 here. If that's a 1, I'm going to assume we're starting out right down here with a low clock. So let's look at a 1 here. A 1 here goes to the other side of this bubble to be a 0 and a 1 there are a 0, and the light is off. So the light is off. This is a 0 right here. We're on a 0 right here. So remember, this was a 1 here. So it's on this state right here. Basically, it must have clocked in a 1 from over here. Okay. So now the switch or the clock goes up. When the clock goes up, it turns this gate to a low. When a low goes into one of these D latches right here, then it clocks in whatever's over here, and that becomes what's on the output and what's stored in this little memory here. So this is a 0 here, so a 0 pops out over here. So that's what we have. We have a 0 right here. We're still at a 1 over here. But now the clock goes low. When the clock goes low, it takes this 0 right here and stores it out here. It's stored in this memory element. That becomes a 0 there. It makes it a 1 on the other side of the little bubble. A 1 and a 1 is a 1, and it turns on the light. And now the light is a 1. And when we go to the next thing here, when we go high, it takes that 1 and it clocks that 1 into this flip-flop, and now we have a 1 right here, but still, remember, there's a 0 there, so the light's still on. And then when it goes low, then this guy right here will then turn off the light. So that's a simple finite state machine example for you. So let's think about this. Storage elements. Each master-slave flip-flop essentially stores 1 bit, or 1 state bit. It keeps it. There's 2 states in that last example, on and off. If you noticed, the light went on, the light went off. There was 2 states. So the master-slave flip-flop, each one of those, as the clock went from high to low. So the number of storage elements or flip-flops, those are the each the master and the slave is flip-flop, is actually we need to keep the next state and this state, so that's kind of the simplest state machine we had. So the number of storage elements, flip-flops, is going to be determined by the number of states and the representation of each state. So let's look at some examples for different devices that have states and see how many bits we need to store each of those states. How many bits do we have? Essentially, last time we had 1 bit worth of data because there were 2 states. 2 to the 1 is 1. There's 1 bit worth of data. 1 bit can be a 0 or a 1, and that's what we were seeing last time. So how many bits, each flip-flop stores 1 bit. How many bits do we need to store? So if we had 4 states, we'd need 2 bits. That would be at least 2 bits, and generally we don't want to waste bits or waste flip-flops, so we do 2. That's the minimum we could do. Basketball scoreboard has a lot more bits necessary, maybe 7 bits for the score, or they say 5 bits for the time, 6 bits for the seconds, or 5 bits for the minutes, and 1 bit for who's got the possession, and 1 bit for halftime, and who knows what else, you know. Blinking traffic sign, that's what we want to do next, is our next example. It has 4 states, so you can do that with 2 bits, so that's 2 master-slave flip-flops. Let's look at that. So this is a little quiz for you to look at, and we want to design a state diagram for this blinking sign. And the way it works is when the switch is off, there's no lights. When the switch is on, the first starts out with no lights, and then it goes to 1 and 2 are on, then 1, 2, 3, and 4 are on, and finally 5 are on. And a little hint for you, how many states have you got? So I'll stop here at this point. I guess there's going to be one more lecture on digital logic.